Now he is. All right, so this is, I did it out of sequence, so this should be the first one, the fundamentals, where the idea is how to get the best possible recordings, and this is going to be about noise and interference, and I'm extended it a little bit. So again, we do these intra and extracellular recordings, and you can all agree that this specific example here is particularly nice. So it's so beautiful. And the question is, like, what do we actually have to do to get recordings like this? And I want to spend some time to really step back and define the problems that we have to solve. And so let's talk a little bit about sort of fundamentals of electricity or bioelectricity. So if we have a cell, not just neurons, we have an asymmetric distribution of ions between the extracellular fluid and the cytoplasm, right? We have these selective ion channels that the ions can go through, and then we have a phospholipid bilayer that acts as a capacitor. So you end up with equal and opposite charges accumulating on the outside and the inside face of the membrane, and that gives us a membrane potential. So that electrical potential difference between the outside and the inside, or inside and the outside, is a voltage. And the movement of these ions through these ion channels is a movement of charged particles, and the definition of the movement of charge by definition is a current. And the ions, at least by passive diffusion, can only go through the membrane by using the path through these ion channels, because the long fatty acid tails of the phospholipid bilayer is completely unpolar, so the membrane is a good insulator. So we can use there's limited permeability of the membrane to ions, and we can define how difficult it is for ions to flow across the membrane as the resistance, right? And obviously the relationship between voltage, current, and resistance is given by Ohm's law, which says that the voltage is proportional to the current and proportional to the resistance, and the current is proportional to voltage and inversely proportional to resistance. So the higher the resistance, the less current you get. And the resistance gives you the relationship between voltage and current. So it's basically, it's the slope of the VI curve, right? So hopefully this was news to absolutely no one here. But it's interesting to look at the scale of these things which we're operating in. And just for reference, let's look at household gadgets first, right? And small ones. So let's say in household gadgets, mostly we operate with constant voltage sources, either from the wall outlet or from batteries or something. So we can connect a voltage source to some gadget that has a resistance, and then current flows. And let's say that voltage source is a battery and the gadget is a tiny little light bulb or something like that. Then Ohm's law tells us that the current that flows in the circuit is the voltage over the resistance. If this is a 9-volt battery, and let's say at this voltage that light bulb has a resistance of 6 ohms, then 9/6 are 1.5, and we're measuring what that, the current is 1.5 amperes. And that's the scale, even at this very moderate kind of tiny little things that we're running here, that household gadgets operate in, right? So we're talking about amperes, volts, and ohms. That scale is very different at the level of neurons, where we measure membrane potential in millivolts, so 1,000 times smaller. Well, the resting membrane potential is tens of millivolts. Synaptic potentials are millivolts. The biggest signals that neurons produce are just about 100 millivolts, right? If you're sitting at minus 70 millivolt, then you go up to like plus 30 or something like that. So it's still, I mean, it's smaller, but not super substantially smaller. But the currents underlying these voltage changes are very, 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 very small, right? So if you look at single ion channels, let's say the ones that underlie an action potential, we have this voltage-gated ion channels, and the single channel currents. So these channels flicker, open and closed, and the current going through these channels is at the scale of picoampere, so a trillionth of an ampere, right? And then you have the whole neuron has thousands of these, but you still just at the scale of a billionth of an ampere, so nanoamperes. This is a bad example actually, because the sodium current can go up into the microampere range, but you get what I'm saying. So we're measuring in billionths of amperes. So that means that we have tiny, tiny, tiny little currents that produce still relatively decent sized voltage responses. And the reason for this, according to Ohm's law, is that neurons are very bad conductor. The neural membrane is a very bad conductor of electricity and has a high resistance, a very high resistance. And we can look at the scale. So the resistance is voltage over current. Voltage we measure in millivolts, so 10 to minus 3 divided by 10 to minus 9 amperes, so nanoamperes. 10 to minus 3 divided by 10 to minus 9 is 10 to the 6, so millions. So we're measuring, the resistance is millions of ohms, mega ohms, right? So the reason I'm going through this is that has some consequences, that we're operating at these scales because these tiny currents, when we want to measure voltages, we have to use probes and circuits in our amplifiers that need to have very high resistances. And if you have probes with very high resistances, that means you're susceptible to all kinds of small interfering current fluctuations, for example, from the radio waves that are in the air, the building 60 hertz AC circuits, and they cause noise, interference and noise. So it's another way to put this would be the signals are so small that they're at the same range as sort of like the stuff that's in your rig anyway, or in the room that you're sitting in. So we're measuring signals that are potentially really degraded by different types of noise and interference. Here's the 60 hertz, and here's the high frequency noise that you get from radio waves, for example. So that means we really have to take measures to achieve a good signal to noise ratio. So we need to be careful about these things. So what do we do about noise and interference? There are two things that we do up front, which is in setting up our rigs, whether that's grounding and shielding, which I'm going to talk about a little bit. And then if that's not entirely sufficient, then we can resort to frequency filtering. And then I want to spend some time talking about our extracellular recording technique, which is differential amplification, where the recording technique that we're using itself is containing a noise reduction feature. Okay. All right, so let's start with grounding. And yes, this is a literal dad joke here. What does grounding mean? It just quite literally means that you connect all your gadget that you have to the literal ground by ramming a big copper rod into the earth, into the ground. You don't have to do this yourself. Someone has done it for you. When you connect rack equipment, at least, and use a 3-prong power plug here, then you're automatically connected to the ground outside, right? So what does this do? Basically, it's useful to think about this. You're connecting small pools of electrons, which means all of your equipment and the sample and so on, to a practically infinite pool of electrons, which is the Earth, or I should say infinite pool of free electrons. Why is the Earth an infinite pool of free electrons? Because it gets charged all the time by sunlight and lightning strikes, right? So, but what does it actually do? And there's a million sort of flawed analogies around. I'm picking one specific one here. So if we look at this picture, at this level here, the big pool, everything is quiet and at the same level. And you can observe things in the water, right? You can see little fishes swimming around there or whatever you are interested in. Whereas up here, you have these series of smaller pools that are all at different levels. And that causes a current between them, which obscures whatever you want to observe in the water. So that's the sort of the crappy analogy. But it basically means if you had ungrounded separate pieces of rig devices and they're differently sized pools of electrons, that would cause a current between them that is not any of the currents that you're actually interested in, and that causes voltage, noise, and interference. So basically, by connecting everything to the ground outside, you bring everything to the same reference level, and the ground then serves as a common reference level of electrons for all the equipment and the samples. So you know, currents across different components that would make noise, you get rid of those. They're eliminated. Another way to look at this with another one of these hydraulic or aquatic analogies would be, think of like throwing a pebble into a glass of water or a cup of water. From the perspective of the cup, that disturbance that you would get is significant, right? But if you throw the same pebble into the ocean from the perspective of the oceans, that's barely a blip as a signal. So that's the overall idea. Practically, you have to be careful about a couple of things when you ground equipment. And the one thing that is the sort of weirdest and the sort of a common rookie mistake to do is to create ground loops. So if you have two devices that are ultimately part of the same circuit and they're both grounded, but they're taking a different path to the earth, if those two paths to the earth are different enough from each other, then you get an extraneous current between these two paths, and that's what a ground loop is. The easiest way to make a ground loop is actually to connect two pieces of outlet connected gadgets, amplifiers or something, to do two different electrical circuits. That's not going to happen to you because when Farzan and Jorge helped design these lab and the floor plan, the four rigs that you have at each of these stations where that scaffold is coming down with the electrical ones, all four of them at each of these places are on the same circuit. So you'd have a hard time to connect different pieces of equipment to different circuits. So I think from that perspective, we're safe. So what do you do practically? So the rack equipment, so the stuff that has a power cord attached to it, is pretty safe because it's grounded through the power supply, right? Through that third lead in the three-prong connectors here. There's a possible exception that some of these chassis, like the boxes the circuits are in here, are not grounded and you should separately ground it. Usually you don't run into big problems with that. You go at the back of these, some have these little nuts and bolts where you can attach a wire to and ground it. It says like G&D on it or something like that. So if you connect everything that's in your rack to the same circuit, you should be fine. If you want to be really super careful, only use one connector, a single outlet, and then have a power strip with multiple outlets in it and connect everything to that so you don't get any ground loops. But you have lots of stuff in your rig that doesn't have a power cord. Things like the manipulators, the microscope, the light guides, even your tubing and all of that. And all of this potentially could serve as an antenna for noise and interference. So you have to ground these things separately. And the way to do this is in principle this. So in my lab, I had some shop made these copper, brass rods with holes drilled into them that fit the banana plugs here. So every single piece of equipment that you want to ground, you just connect, everything converges onto this brass rod, and then the brass rod is grounded with a single path. And the way to do this is that some of the equipment that we have, the AM systems amplifiers and the Brownlee amplifiers, have a ground socket in front that basically connects to the same ground as the three-prong connector is attached to. So it's a single point to go to ground. So the principle is always try to take for each piece of equipment that you want to ground the shortest path to then a common path to ground where everything goes through. So that way you don't get any ground loops and you don't get any interference from that. Particularly ground loops cause this big like 60 hertz feedback for some reason. So that's the safe way to do this. The three of us all probably have different ideologies on how to do grounding. I know that Farzan likes to ground one by one while he has a recording until the noise is gone, and that's fine. I'm more of a guy, it's like I'm grounding everything up front that I can think of could possibly cause noise, and then see what it does. But it doesn't matter. But in the end, that's what you'd have to do, and you have to avoid ground loops.
I have a question.
Yeah.
Okay, when you say shortest path, you mean the length of the banana clip?
No, that's not that important. but it's not to do any loops and not to sort of do things in parallel and then, you know, yeah. But it's, yeah, I mean, but there's also something to be said to not connect your manipulator that sits 20 centimeters away from that brass rod, not to connect them with a 6-foot cable. That's just a practical thing. All right, so the other thing that we may have to do, and we have to do to some degree, is shielding. What does shielding mean? In general, it refers to the phenomenon of the Faraday cage, right? Michael Faraday described that if you put a hollow electrical conductor into an electrical field, all the charges stay on the outside because the resistance path is smaller along the surface, and there's no internal electric field, and Mr. Faraday here is safe inside of it. So sometimes that's a literal cage we're talking about, and sometimes it's other types of shielding. So you may have seen this in the most impressive demonstration of this is at some signs. Why am I having my hand up? I don't know what I did. Anyway.
When you wave your hand, sometimes the signal.
I see. Can I do this and then it goes down?
It will come down if I don't know.
Anyway, so the science museum or exhibition here, these big Tesla coils here that produce very, very high voltages. You're safe if you're in a little metal cage in the middle because all the charges stay on the outside. The not so fun application principle of this is if your car gets a direct lightning strike, as long as you don't touch any metal, the car is a Faraday cage, so you won't get electrocuted. You know, your tires may melt and the engine may go up in flames, so ultimately you may die anyway, but not from electrocution. All right, so at the rig, there's sort of like 2 or 3 levels of this. The first one is the literal cage. So these vibration isolation table manufacturers want to sell you these fancy cages that are made of like gold-plated wire mesh, the walls here, for noise reduction and shielding, and they cost an arm and a leg. Right? So if you need them or not for your recordings depends very much on what kind of building you're in and what the local conditions are. And it turns out that for CKB, it's not a big deal. So neither Farzan nor Ho will use any Faraday cages on top of it, and it's fine, right? So you can get rid of all the noise, most of the noise without that. I have them because I needed them in Florida, and also because I had them made by a shop from these aluminum plating, and it's just nice that you get these dark boxes, right? So if you want to do any fluorescence applications, dye fills, or photo ablations or something like that, it's just nice that you have the possibility to do everything in dark room, basically. But yeah, but as a noise reduction thing, you don't really need Faraday cages in CKB, at least not on the 4th floor. I'm not so sure about the 3rd one when we run the course, but where we all use shielding is that, with the exception of our handmade extracellular electrodes, all the cables that we used are shielded, particularly the coax cables that the BNC connectors are attached to, and these 5-pin AM systems extracellular cables. And shielded cables look something like this, right? You have however many inner conductors are in there. They are insulated from each other with plastic, but then those are all wrapped twice, once in basically a foil, aluminum foil, and then in this braided shield, so it's braided wire. And then if they're fancy enough, those shields are then actually also connected to the ground, at least in coax cables, and then there's an outer sheath. So if you have a whole cable salad at the back of your rig, or they're all twisted around each other, it's not a problem. You will not get interference because they're all shielded. For the extracellular thin wires, you have to be a little bit, it's usually not a big problem. You have to be a little bit careful that they're not all crisscrossing on net. They're not going over your light guide or something like that. So you can pick up noise with those. And then there is the tinfoil head crazy person approach that we all have to take to some degree, in the same way that tinfoil heads protect you from, what is it, alien mind control or government mind control or both or whatever. We have some pieces of equipment in the rig that you can't just ground because they don't have metal surfaces, either because it's some plastic wrapped piece with metal inside of it, or because these are the lines with silane, which means that you're running electrolytes, which conducts electricity, but it's in polyethylene or silicone tubing, and so you can't just ground it. So we wrap them in aluminum foil, and then we can ground the aluminum foil. So that's the type of shielding. You shouldn't need to ground them, but just do it to be careful. They don't have to go all the way. It's usually sufficient to just have them in the close vicinity of where your dish sits, but that's another part of the shielding. All right. So if you do all of this and you do the best possible job that you can, you will eliminate sort of most of the really nasty noise that's in the room, and maybe even comes from your own rig equipment. But that's not necessarily always good enough. And if it's not good enough, you can resort to filtering. So what does filtering mean? To understand a little bit about filtering, we sort of should very briefly talk about frequency components of time variant signals. This guy here, Joseph Fourier, figured out a long time ago that you can basically reconstruct any complex signal, no matter how complex, by adding up different sine waves with different frequencies and different amplitudes. And the inverse then is also true. You can use mathematical methods. You may have heard of the Fourier transform to decompose a signal like this into its frequency and amplitude components and generate a spectrum that shows you how much power that signal has at different frequencies. Right. So the point here is that if we have these complex signals, some of the frequency components in there are the ones that we are interested in because they come from the neuronal signals, action potentials, and so on. And others are frequency components that we're not interested in, the noise and interference. And if we're lucky, to some degree at least, those are different enough that we can try to separate them. And that separation of different frequency components is exactly what frequency filtering is, right? So here are the 4 basic types of frequency filters. This one is a low pass. Low pass means that it's a filter that lets low frequency components pass with full amplitude and suppresses the amplitude of high frequencies. High pass means that it suppresses the amplitude of signals with low frequencies, but lets higher frequencies pass. Band pass means suppresses amplitudes of high and low frequencies and has some frequency band in the middle that it lets pass. And notch or band stop filter is the opposite of that. So it suppresses the amplitude of some intermediate frequency band. All right, so sorry, these are teaching slides. So we have filtering is everywhere, right? So these are some everyday examples. If you ride your bike over cobblestones, the suspension and your air-filled tires act as a low-pass filter. So you experience very little of the high-frequency vibrations from the cobblestones, at least much less than you would if you'd use a solid metal wheel. But it doesn't do anything to your experience of going uphill and downhill through the streets, right? So the low frequency components are not affected by that. Same way, if your neighbor blasts loud music, your walls act as a low pass filters, and the thumping bass is a lot louder than the screeching guitar solo or something like that. And the opposite of that is your phone speakers are high pass filters in the sense, like I'm not with earplugs in it, but if you just play music on your phone, those tiny little speakers are not sufficient to produce a lot of power in the bass range, so you get this scratchy, scratchy sound basically. So the high frequencies are louder than the low frequencies. And then an example for bandpass filtering is your car radio, right? And it's actually double bandpass filtering. So the radio stations put out their signal at a narrow frequency band to not interfere between the different radio stations. And then your radio lets you pick narrow frequency bands out of this so you don't listen to several stations at once. All right, let's look at actual sort of time variant signals here. So if we have, let's say, this step signal here, according to Fourier, that near instantaneous jump to a different level would correspond to a very high near infinite frequency or very short or like near zero wavelength, right? Whereas the flat part would correspond to a very low frequency, near zero frequency, or a almost infinite wavelengths. So if we use a low pass filter on a signal like this, it will not let the high frequency, go suppress the high frequency components, but will not suppress the low frequency components. So you get a signal like this, which is a classic sort of waveform of an RC filtered signal that is relevant for all kinds of things because membranes have properties like this. But this is just an example here. With a high pass filter, it would be the other way around, right? So that one will let the high frequency components through, but suppresses the low frequency components. Now, the more useful way to, in terms of like practically what filters to use, to look at is maybe this chirp. So a chirp is a sine wave with changing frequencies. In this case, it's a linear increase in frequency of the sine wave, right? So that's, let's say this is our input signal here. The amplitude is the same everywhere. Now, if I low pass filter this signal with some settings that I will say something about in a second, it doesn't suppress the amplitude of low frequencies and suppresses more and more the amplitudes the higher the frequency becomes. What you see here is that this is not a very tight cutoff filter, right? So it's a gradual process here when you apply a filter like this. So this filter type is, you may have heard of these words like Butterworth and Bessel and things like that. Don't worry about it. There's different math behind it. And then there's an order which describes the steepness of this function, and you put in a corner frequency, right? So here it's at 100 Hertz, but it's not very abrupt. I can make it steeper, this function, but this is about as steep as I can make this kind of filter without the filter becoming unstable and then doing crazy things in different frequency bands. And so this is about as sharp a cutoff for frequencies as I can create here. And the same is true for high pass filter. So if you use a high pass filter, you suppress the low frequencies, but not the high frequency. Again, this isn't particularly steep. This is about as steep as I can get it. So there will be some bleed through and overlap and things like that. It's not that you can just decide, I don't want anything below 100 Hertz or above or below 300 Hertz or something like that. So it's a gradual function in all cases that you apply these filters to. And then you can make, this is about the best bandpass filter that I can generate. This is about, so it suppresses low and high frequencies. And this is a notch filter that just suppresses as an intermediate frequency band here. All right, so practically this means we have our neuronal signals with different signal components, right? The things that we actually are interested in, I don't know, EPSP, spikes and all of that. You may have some low frequency noise, like baseline drift, basically, and some high frequency noise from radio waves or something. So what you're actually recording is that resulting signal that has these different components in it, and we can try to separate it with filters. So if you, in this case, use a high pass filter, you can suppress the baseline drift, so the slow component is gone. If you use a high pass filter, you can suppress the HF noise. And if you use both, so practically, not technically, but practically you're using a bandpass filter, then you can get a signal that is as good as you can hope for in its correspondence to the actual neuronal signal that you're interested in. Right? So what does this look like in your rig? Some of this you can do upfront, and some of it is also almost automatic. So for our extracellular amplifiers, they have each of the channels has these knobs and dials on it, and I color coded them here. It has for some reason they call this the low cutoff filter, which is a high pass filter, right? They have a low pass filter that they call a high cutoff filter. There's a gain button, and then there is a on and off notch filter in here. And here's the what's called the Bode plots, the amplitude over frequency of that amplifier. So the pass band, how much amplitude you get depends on the gain setting, right? But then you get the low cutoff. So there's your high pass filter that you can change, where you can right or left shift it between 0.1 hertz and 300 hertz. Then you have the low pass filter, the high cutoff filter that you can change left and right from 500 to 500 hertz to 20 kilohertz. And then you have this notch filter that is relatively narrow, not super efficient, but tries to cut off some of the 60 hertz noise that you have still in there. I'm not a big fan of using notch filters to begin with, but that's a different discussion. So that's something that you should look for. I wish I had, if I had a extracellular one to play with, maybe at some point we should record these different filter settings, what the same recording looks like. I haven't had time to do that, but this is a realistic setting that we use to get our best signals. You can play with these filters and see what it does to your sort of low frequencies and high frequency components and how much it suppresses the amplitude of the actual signal and things like that. So this is not a realistic recording that you do. It's highly filtered to begin with. You don't have any other choice, right? So there are these filters inbuilt here. What about the intracellular ones? Basically, I say up front, don't do anything. So the 2B has a filter wheel here, but that is basically just for the first channel, the channel 1 and the associated current output. And it's only really in there because you can do some applications we don't use, like discontinuous current clamp and single electrode voltage clamp that has internal high frequency switching, which causes high frequency noise. And basically this thing is there to suppress that and not the usual noise that you're dealing with. So don't touch this basically. The 9A, the scaled outputs have filter settings. The high pass ones default to DC, which is a zero frequency sort of offset filter. And the low pass is defaults to 10 kilohertz corner frequency. I would not touch those. Remember, if you use filtering while you're recording, that's it. You record a filtered signal. You can always, if you're not sure, do filtering later after the fact, after you record it, right? So I would keep these at default settings and then filter after the recording. So any of the softwares that you may be using, pClamp or Spike 2 or what have you, will have some way to filter traces. So in this case, it's a step voltage and current. I forgot what this is from, but maybe you're not happy with the noise level here. And there are some very cheap ways to do instantaneous filtering. In Spike 2, for example, you have things like an average or medium or mean or median filter. So that one basically just takes each data point and replaces it with a median of a bunch of points around it. That's a simple way to do low pass filtering, so it gets a lot better. And then you have, in pClamp, you have, I don't know, Bessel filters or something like that, that you just, I think you just press a button or something. Do I remember this right? Yeah. And you have whole fancy filter banks in Spike 2 too, that are the ones that I showed you with the chirp, the chirp function. You have to be a little careful. My strategy with filtering is this: you do have, if you have something that has frequency components that you want to filter out. This is a PD axon recording where the stimulus artifacts from stimulating the nerves to getting these action potential responses was pretty big. The stimulus artifacts are much faster than the actual X potential, so we can do some low pass filtering. So I low pass filtered this, and you see that the stimulus artifacts get a lot smaller, but then I can put these two traces on top of each other, and you see that you really only suppress the high frequency stimulus artifact components, but the actual action potentials are not affected. If you get too ambitious, you say like, this is still bigger than I wanted to be. and crank up the time constant low pass filter more, basically, this gets much better in terms of the artifact. But you see what happens to the actual signal here. You put them on top of each other, you actually screwed up your signal, right? So you messed with the amplitude because these filters are not very steep, and because the frequency bands of this, the artifact signals and the actual biological signals may overlap. So I would always, if you do this kind of filter, I always sort of copy a channel and apply the filter to one and put them on top of each other and check that I'm not messing up the signal I actually want to show. All right. The last thing to talk about differential amplification, I want to use as an excuse to talk a little bit about extracellular recordings. So what do we actually do when, yes?
Can I ask, before you go, the filtering not only changes the amplitude, right? And that's also important when you are looking at things like, for example, activation curves or whatever. The filter will change the slope of the signal. So it's not just amplitude, but it distorts the signal.
If you want to measure time constants of decay and things like that, and you low pass filter, then they all become a lot bigger, right? Yeah. All right. So when we're recording it, what I say is an exponential, right? So we have our membrane that separated charges, positive on the outside that accumulate there, negative on the inside, that's at rest. And if you have an action potential come through this axon, then that polarity briefly gets inverted, right? So it basically looks like this. All right. So if we record this intracellularly, I can ignore the positive charges on the outside because we're measuring the intercellular signal with respect to the grounded path, right? So we're measuring the actual voltage. So that change, you know, that brief reversal to a positive potential, and then you go back here. So that's technically difficult in terms of putting in a small electrode into an axon, but sort of theory-wise, pretty straightforward to understand, right? But we can also look at the outside charges, and there, the perspective is you have positive charges in the unexcited membrane regions and negative charges in the excited membrane regions. And that actually means that you have an electrical field, right? And that electrical field is caused by the fact that the unexcited membrane regions act as a source of electrons, and the excited one is a sink of electrons. So you have an extracellular electrical field, and you can measure it. So if you, and we're not doing these kinds of extracellular recordings, and it's a special application, but you can basically use a point recording, like a glass microelectrode, and instead of sticking it into the axon, you keep it close to the surface of the axon. Now, if you have an action potential approaching, it's not at the electrode yet, then you get this electrical field, and your electrode is in the part of the electrical field where electrons move away from your electrodes, and that gives you a positive signal. Then a little while later, the action potential will arrive underneath your electrode, and then you're in a part of the electrical fields where electrodes move towards the electrons move towards the electrode. That gives you a big a negative change in the potential. And then the action potential moves further away, so you get a positive potential again, and ultimately dissipates when it's gone. Right? So that's what extracellular potentials are. So you have an intracellular potential where you actually measure the membrane potential, and these extracellular signals that are basically changes in the extracellular field potential. And for those interested mathematically, those extracellular potential from point recordings are basically the second derivative of the intracellular waveform. So it's the slope of the intracellular function, if you will. Not important right now, but what I do want to point out is that while the intercellular signal is about, let's say 100 millivolt, like let's say we sit at -70 and go up to +30, the extracellular potentials are much, 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 much smaller, typically around between, let's say, 1 microvolt and 1 millivolt. So that is a problem on its own. Oh, now I held my hand up again. Just in terms of signal to noise ratio, right? I want to take somewhat of a detour here to say a couple of things about extracellular potentials. But so this is a point recording. We're not doing point recordings, right? We're doing this, for example, these wells, and I stick wire into it. If you have a recording where you have a cut end of a nerve in a Vaseline well, it looks pretty similar to this. It may be a little more time variance or a little broader because you know, the action potential is still traveling and things like that. But it's basically going to look like this. But we're also doing these what's called en passant recording, like your LVN recording, where then the action potential enters the well and then leaves the well again. And there's something funky happens, which is you basically get the same signal as here from the action potential entering the well, and then you get the inverted potential from the action potential leaving the well. How much overlap is between these two signals depends on how big the well is and how fast the action potential travels, right? So you can get scraggly. So if you look at in detail at your LVN recordings, chances are that there's more than this, like going up, down, and up again, but you have like several peaks in them and they look pretty complex. All right. Another side note, if you have, let's say, 2 different axons that are identical in their specific membrane properties, but different in size, if you record intracellular action potential from those, they should look the same. They look the same because the intracellular potential only depends on the relative expression levels of the sodium and potassium currents, right? And the way that determines how you go in between the equilibrium potentials for sodium and potassium. Now, the larger one of these axons has more ion channels and a lower input resistance. So the currents that are generated and needed to move the voltage in that range are bigger than in the smaller one. So you have bigger currents, which doesn't make a difference for the intracellular recording, but bigger currents means bigger field potential changes for extracellular recording. So bigger axons produce bigger extracellular spikes than smaller ones do. It's not the only thing that determines the amplitude of them. It's, you know, sort of the geometry or where your electrode is. But then I think the most important one is how insulated the axons are. Even if they're not myelinated, they're wrapped in glial cells and things like that. So for example, I have not seen any convincing evidence that the reason the LP spikes on the LVN recordings are so much bigger than everything else is because the LP diameter is much bigger. It's probably less wrapped or something. We don't know, but so there's different things that determine this. Other side note, if you do 2 synchronous intracellular recordings from these 2 axons, you get nice separated traces. But if you do an extracellular one, you record both field potential changes that are induced by the intracellular spikes from both of these axons, right? And that's can be a curse and a blessing. So you can record, and they're even distinguishable by amplitude here. But if they happen at more and more the same time, they summate and obscure a couple of things. So that it's nice that you can record the whole pyloric rhythm and its phasing just with a single LVN recording, but it's a pain that you can't determine what the spike frequencies of PY neurons are because all 3 to 5 of them are on your same nerve recording. And here's an extreme example. The extreme examples of this is I forgot what the textbook entry here was, but so this is limulus optic nerve where someone actually pried away a single axon, put it on a hook electrode, so you can isolate a single potential, get the spikes from that optic nerve axon, and shine different amounts of light on here and so on. That's one end of the spectrum. The other one is where you actually make use of this phenomenon is like, most extreme one I can think of is the EEG. These are human EEG. So you put an electrode on the skull, basically, and you record thousands of neurons at once. And if they're sort of randomly firing, then you get this noisy signal. It's not noise, though. It's actually from the recordings you can tell, because when the patient dies, you get a flat line here. So it's a little harsh.
Matter, for example.
Just that's dead. But it makes sense because you do get signals if many of the neurons that you record from fire at more or less the same time and shut up at more or less the same time. So if there's coherent activity across large numbers of neurons, you get signals. You get these oscillations that can correspond to, let's say, epileptic seizures, gamma oscillation, like brain waves, gamma oscillations, spindle oscillations, all of these kinds of things, right? In this case down here, it's like this is probably from the back of someone's head, and you switch on the light, and then lots of neurons start firing at the same time, lots of neurons shut up at the same time, and so on. So you're actually making use, there's not much information in what these single neurons are doing. You got information about what the level of synchronization across many neurons is. All right. That was just a sort of like a distraction about what extracellular recordings are. Just basically because I had these slides. Let's go back to the noise thing.
Wait, I have a
Yes.
question
Yes.
before we move on. Okay, so a couple of slides ago, were talking about the size of the whale. So the smaller the size of the whale, the better it is.
No,
And
you get
bigger?
bigger signals from
Oh.
bigger wells, but no,
Oh.
all that, wait, where is it?
Yeah, this one.
So this is the point recording. If you have a big well with like this, for example, you get more separation between these two different signals. I would build decent, I mean, you don't want gigantic wells, but I've seen many of you building wells that are smaller than they have to be. Right? I wouldn't worry too much about it.
And then for we have a reference electrode that goes inside of the well, and then the ground electrode that goes outside of the well. Does it matter if,
yeah,
what is it called?
I'll talk why we're doing this in a second.
Okay. All right.
So the point from going back to noise is these extracellular potentials are 100 to 100,000 times smaller than the intracellular ones, right? So which gives us a big problem in terms of signal to noise. And the solution to this is somewhat inherent in the recording techniques we're using. If you look at our extracellular amplifiers, they say that differential AC amplifiers, forget about the AC part, but the differential amplifiers. And what does this mean? So here's a differential amplifier and the way we use them, right? We have two leads. One we put into our well that isolates a piece of nerve from the grounded bath. Well, the bath doesn't actually have to be grounded, but and then we have a second lead that we put as close to that recording well as we can, right? What does this do? Well, let's look first on what the signal is that our first lead actually sees. So hopefully it sees the signal that we want to record. So the activity in that nerve or in that specific axon or whatever is going on there. Let's blow it up a little bit. So we want to see something like this. The problem is that this signal, as I just said, is tiny, right? It's probably in the microvolt range. And that means that at the same time, that lead picks up a lot of noise. And the noise probably is at least an order of magnitude or more bigger than the actual signal. So I'm kind of like underrepresenting it here. So what the first lead sees is basically a signal that is completely obscured by the level of noise. That's where our second lead is coming in. Our second lead is not insulated from the so it doesn't pick up any neural signal. It's just sitting in the bath, but close to it. So the ubiquitous noise, the noise doesn't come from the nerve, right? It comes from the rig. It's everywhere in your rig. So it picks up that noise signal. And if they're very close geometrically, then you would think the noise that the second lead sees should be almost identical to the noise that the first lead sees. The only difference between these two leads is that one gets the biological signal and the other one doesn't. So I could use that noise signal, this noise signal, to subtract it from that combined signal, and I should end up with just the biological signal. And I don't have to do this in a fancy electronic way or on a computer later, but a differential amplifier is called that because it amplifies one of the leads with one polarity and the other lead with the opposite polarity. So everything that is identical between the two leads cancels each other out. So it's the same as just subtracting this noise from the signal noise, and you end up with just the signal. I blow this up. It's not going to be perfect. There's other inherent noise sources, and the signal on both of the leads is not going to be 100% identical, but that's basically what we're doing. Right. Does that answer your question, Shakila, or was there an additional thing to that?
So, and also, does it matter that lead 2 for it to be like super close to the Vaseline well?
Well, in theory, you want noise that you pick up on lead 2 to be as identical as can be from the one. So I wouldn't put it in the other end of the dish. But if you're asking me, does it matter if it's half an inch away or 3/4 of an inch away? I would say no. You just put it in where you don't like mess up your prep or something.
So can I make 2 more comments here,
Yeah.
or just maybe at least one? So the other thing, so I'm not actually contradicting anything Dirk said. Everything he said is correct. But the other thing on this amplifier that we use for extracellular is that it's a differential AC amplifier. So the AC means that on the leads, it also has a capacitor. I don't know if that's, I mean, if you want to go any more into that, Dirk. And that capacitor allows the subtraction of any actual DC voltage. So it only measures changes in voltage. It cannot possibly measure actual values of voltage.
There is a reason why it's called AC amplifier from the circuitry too, but it's not, don't think of it actually in the same way as you think of direct and alternating current from like power supply, but it's that basically it's a zero offset kind of arrangement. If you put the low pass filter all the way up, I guess, which we in the chorus did for recording EKGs, you will get low frequency oscillations too that are pretty slow, but like big offsets and drifts and things like that are impossible with AC amplifiers. That's what they're designed for. Right, that's basically it. So things to keep in mind is, oh wait, you said you had 2 comments.
Well, the other one was about the size of the well, because that's something that Shakila asked. And I think generally speaking, the bigger you make the well, the bigger the distance between the 2 components of the signal that goes through it. But if you're recording, let's say, from the end of a nerve, it makes absolutely no difference how big your well is.
But it is also the size of the field, right? So if you make the well bigger to some degree, you get better signals. It's just that temporal separation gets weird. But it's, I mean, it's just a convenience thing. It's like, it's fine to build a well that is like almost a centimeter in diameter. You don't have to do them like super tiny.
Yeah. By the way, wells were introduced relatively more recently than the recordings that we did. We used to put 2 leads next to the nerve and just push Vaseline around it without having any well in between. I think Pierre Meron is the one who introduced the well recording.
So in insects, which I grew up with and Nelly grew up with, I guess, you do a lot of these nerve recordings in the intact animal. So you use hook electrodes and you make some metal contact to a nerve, and then you insulate that whole thing with like a ball of Vaseline, basically. And I guess because most invertebrate people used to do that. I didn't know that like who started it? Oh, Pierre Meron. Like this, so this was actually
Pierre Meron started the wells. Yeah. Before that, we just put 2 electrodes next to the nerve and just pushed Vaseline around it. Just like,
how terrible is it?
It's actually much better if you manage to isolate it properly. It's just that the well is easy to check with a drop of saline.
So it's a pain in the, so in insects, you are very lucky if you can lift the nerve out of the saline and then do this. If you have to do it under saline, it's very hard to get a good isolation basically from the Vaseline. So I'm guessing
I
if
see.
you do it in the dish, it's difficult. Anyway, so most powered equipment that's sitting in your rack is grounded through the outlets. So you must potentially ground but you must ground everything else that isn't, potentially everything, not necessarily everything, that can serve as an antenna for noise and interference. And this includes these non-metal parts like saline tubing that you may have to shield with tinfoil hats, basically, and then grounded. Yeah, avoid ground loops, right? So the shortest path to common path to ground is what you should be aiming for. And then filtering, if you use filtering, be careful, like have a good reference, make sure that the filters don't alter the signals you're interested in. And as Jorge pointed out, not just the amplitudes, but sort of the time course of it, the slopes of depolarization and hyperpolarization, or if it's currents, yeah. All right. That was it. And then I still think not necessarily me, but someone should have a rundown of recording techniques, actually, like a little bit of a background word about voltage clamp and patch clamp and all these kinds of things. I did the extracellular part already, so I think it'd be nice to have at some point.
Yeah, I nominate Jorge for that.
You what? Oh, you nominate Jorge for that.
All right, I'll do it.
I
but-
nominate Jorge for the voltage clamp current.
All right, I'll do it, but not next week.
No, we're gonna be gone anyway.
Oh, you're on.
No
Yeah.
rush.
Good. Yep.
Thank you, Smita. But you always say to everything that it is the best, so I'm taking it with a grain of salt.
No, the slides. How do you make those beautiful slides? Oh my.
Well, it's my hobby. I'm wasting a lot of time on
Oh,
that.
you have to do
Like other people paint at home, I make scientific figures. It's
I think the YouTube community will be so happy. All the